Sample exam 6. This is chapter 6, sample exam. The first one, let's find the Euclidean norm for V. This is the square root of the 2 squared plus the negative 4 squared plus 5 squared plus the negative 1 squared. So we get the square root of 4 plus 16 plus 25 plus 1. And that gives us the square root of 46. Here, using U, V, and W, let's find all of these norms. So the norm of U plus V, this is the norm of the U, which is 1, 2, 3, plus the V, negative 2, 0, 5, and we find this. This is negative 1, 2, and 8. And so we find that norm gives us the square root of 1 plus 4 plus 64. And that gives us the square root of 69. The next one, we found the norm of U minus V. This is the norm. The U is 1, 2, 3 minus V. V is the negative 2, 0, 5. So we get the norm of 1 plus 2 is 3, 2 minus 0 is 2, 3 minus 5 is negative 2. And so that gives us the square root of 9 plus 4 plus 4. So we get the square root here of 17. Part C, find the norm of U plus the norm of V. Well, the norm of U, we take U to be that, so this is 1 plus 4 plus 9 plus the norm of V. It's the square root of negative 2 squared, that's 4, plus 0 squared, we get 0, plus 5 squared, we get 25. And that gives us the square root of 14 plus the square root of 29. And that's it. The next one, we want to find the norm of W divided by the norm of W, basically to examine the nature of the unit vector. So let's first find the norm of W, and W is given to be 7, 1, and negative 3. So that gives us the square root of 49 plus 1 plus 9. So we get the square root of 59. Now let's find here W divided by the norm of W. So this is 7, 1, and negative 3 all over the square root of 59. So now we find the norm of W over the norm of W. This becomes the square root of that 7 squared plus 1 squared plus the negative 3 squared. That's all over the square root of 59 to be squared. So this is the square root of 49 plus 1 plus 9 is 59 all over 59, and we just get 1. And that's what we're supposed to get. So let's move over to the next page. Here, compute all of these inner products. So let's find the inner product of u with v. So this is 1 times negative 2 plus 2 times 0 plus 3 times 5. And so that gives us 13. The inner product of u with w is 1 times 7 plus 2 times the 1 plus 3 times negative 3. So that gives us 7 plus 2 minus 9. That gives us 0. So you can say there that u and w are orthogonal. Now the inner product of v with w. This is negative 2 times 7 plus 0 times 1 plus 5 times negative 3. So that's the negative 14 minus 15, get negative 29. So the only two that are orthogonal is the u and the w. Compute the distances. So the distance between u and v, this is the norm of u minus v. Well, this is the norm if you take u and v, and I think we looked at a bit of that earlier. So this becomes, when you subtract those two vectors, we get 3, 2, and negative 2. And that's the square root of 9 plus 4 plus 4. We did do that earlier. That's the square root of 17. So we got the next one, the distance between u and w. So this is here the norm of u minus w. This is the norm of the u, which is 1, 2, 3, minus w, 7, 1, and negative 3. We do the subtraction there. This is the norm of 1 minus 7. We get negative 6. And then 2 minus 1 is 1. And then 3 plus 3 is 6. So that gives us the square root of 36 plus 1 plus 36. And excuse me, this is 1 minus 7 is negative 6. 2 minus 1 is 1. And then 3 plus that 3 is 6. And we got all the numbers there. So good. So this is the square root of 73. And then the last one, the distance between v and w. So this is the norm. V is negative 2, 0, 5, and then that's minus w, which is 7, 1, and negative 3. So this is the norm of negative 9, 0 minus 1 is negative 1, 5 plus 3 is 8. So we get the square root of 81 plus 1 plus 64. And that's the square root of 146. Okay. So now let's move on. Here we prove the triangle inequality. We did this in class. Let's do it one more time. So we're going to start with the norm of u plus v, and we square that, and that equals to the norm of u squared plus 2 times the inner product of u and v plus the norm of v squared. Now, based on numbers, this is less than the norm of u squared plus 2 times the absolute value of the inner product of u and v, then plus the norm of v squared. And here, this is based on the relationship of numbers. And then this statement is less than or equal to the norm of u squared plus 2 times the norm of u times the norm of v plus the norm of v squared. And this is by the Cauchy Schwarz inequality. And this side here is equal to, this is the simply a perfect square trinomial. So this is the norm of u plus the norm of v, all to be squared. Taking the square roots of both sides produces the inequality that we're proving. That is the triangle inequality. What about to prove the triangle inequality for distances? So we start with what's given, the distance between u and v. That's the same thing as the norm of u minus v. This is with some arbitrary vector w that we add, and then we subtract its translation as well. So we get the norm of u minus w plus w minus v. This is just use the associative property, associate this u in the w plus associate this w in the v. And so this statement here is less than or equal to the norm of u minus w plus the norm of w minus v. And this is by the triangle inequality for norms. And here, this statement there is the same thing as the distance between u and w plus the distance between w and v, and thus we have proven the notion. And it's no more than a notion. So let's prove the Pythagorean theorem. Here we let u and v be orthogonal. So let u and v orthogonal. That is, the inner product of u and v is equal to 0, and this is here for all u and v in the Euclidean n space. So then, if that's the case, then we start with the norm of u plus v squared. Well, you know that this is the same thing as the inner product of u plus v with itself. So this is equal to the inner product of u. We use additivity. So u and u plus the inner product of u and v plus the inner product of v and u, then plus the inner product of v with itself. Now, the neat thing that since the inner products with u and v are 0 because they are orthogonal, this is 0 and this guy is 0. And so what we end up with is the inner product of u and u plus the inner product of v and v. But by definition, the inner product of u with itself is the norm of u squared, and the inner product with v with itself is the norm of v squared. You're done. Let's move on. Here we compute the inner product, part A, using the standard inner product. So the inner product of q and p is, and think about p as being for the coordinates -6, 3, and -7. And then q is 2, -5, -3. So we get this inner product. This is -6 times 2 plus 3 times -5 plus -7 times -3. It gives us -12 minus 15 plus 21. So we get -27 plus 21, or just -6. And we find this norm of p. So this is the norm of the coordinates -6, 3, and -7. This becomes the square root of 36 plus 9 plus 49. And that gives us the square root of 94. What about the distance between p and q? This is the same thing as the norm of p minus q. And so here, this is the norm. P is -6, 3, and -7 minus q, 2, -5, -3. We do our subtraction. This is the norm of -8. 3 plus 5 is 8. And then -3 plus -7 plus 3 is -4. And so that gives us the square root of 64 plus 64 plus 16. And this is the square root of 144. And we get a perfect 12. Well, let's keep on pushing. Here, this is a proof where we just show that this inner product satisfies the 4 axioms for the inner product space. If all 4 axioms hold, then we say that this inner product does define an inner product space on a real vector space. So the 4 axioms that we have were symmetry, additivity, homogeneity, and then lastly positivity. So here, to show that the inner product of u with v is the same thing as the inner product of v and u. So we start with the left side, so the inner product of u and v is equal to, as it's defined, 2 times u sub 1 times v sub 1 minus 7 times u sub 2 times v sub 2. Now, since the coordinates are numbers, you can commute those terms. So this is 2 times v sub 1 times u sub 1 minus 7 times v sub 2 times u sub 2. And that gives us the inner product of v with u. So that one holds true. Secondly, we look at additivity, or you may call it the distributive property. So here, to show that the inner product of u plus v with w is equal to that should be the same thing as the inner product of u and w plus the inner product of v and w. Well, let's see. Let's start with the left side, the inner product of u plus v with w. We can just write this like this. This is u plus v dot with w. And so notice that the terms for u plus v would be u sub 1 plus v sub 1, comma, u sub 2 plus v sub 2, that's dot with w sub 1, comma, w sub 2. And when we work that out, we get u1 plus v1. That's going to be the here the dot product of that with this w sub 1. And I think if you see it, we can go ahead and just do the multiplication. And so I don't want to lose my hand. So this becomes, just want to use that formula since we already have it, right? This becomes 2 times the first component, which is u sub 1 plus v sub 1 times the first components together. And so this is times w sub 1, then minus 7 times both of the second components multiplied, so parentheses u sub 2 plus v sub 2, and then this is times w sub 2. Now let's simplify that. This is 2 u sub 1 w sub 1 plus 2 v sub 1 w sub 1 minus 7 u sub 2 w sub 2 minus 7 v sub 2 w sub 2. Didn't have time to go over this problem in class, so this is good that we can cover it now. Now this is the left side. Now you can commute those terms if you will, or you can leave them like that. I think that's fine, but if you want to write it as 2 times u1 w1 minus 7 u sub 2 w sub 2 plus 2 times v sub 1 w sub 1 minus 7 v sub 2 w sub 2. Now with that statement, that is, if you want to get fancy, this first statement here, this guy is the dot product of u with w. Plus, look at this. This statement here is the dot product of v with w. We get it. I'm done. We went from the left side, and the left side for us produced the right side, right? Too many lines. Thirdly, homogeneity. Homogeneity says that, would say it like this to show, well, what does it say? It says that the inner product of k times u with v, is that the same thing as the scalar k times the inner product of u and v? Well, let's see. We start with the left side and see if we can produce the right side. K times u v is the inner product of that. Well, this is 2 times k times u sub 1 times v sub 1 minus 7 times k times u sub 2 times v sub 2. Now, if I factor out a k, I have left 2 times u sub 1 v sub 1 minus 7 times u sub 2 v sub 2. Now, but isn't that the same thing as k times the inner product of u and v? Again, we've shown that the left side produces the right side. And then lastly, see if I have a little space for positivity. Here to show that the inner product of, let's call it u or v, doesn't matter, but it has to be the same one. So the inner product of v with v, we want to show that this guy is positive, equal to 0, and the inner product of v with itself is equal to 0 if and only if v is the 0 vector. So let's look at that. The inner product of v with itself is equal to 2 times v sub 1 squared. Oh, it's minus, based on this definition. It's a very funny inner product, right? Minus 7 times v sub 2 squared. And this guy has some issues here, because notice that if v sub 2 is greater than v sub 1, we get negative. So this guy would fail. So this is positive or equal to 0 if and only if, and I should say it's positive if and only if v1 is greater than v sub 2. Otherwise, the set fails. Fails here to be an inner product space. Now the 0 is fine. That here, this inner product equal to 0 if and only if 2 times v sub 1 squared minus 7 times v sub 2 squared equal to 0. And that has to imply both ways that v sub 1 is equal here. Is equal to v sub 2, and that they're both equal to 0. And so that's the only way that we get 0. Can you see that v sub 2? So this particular inner product would fail because of this statement right here. Right? If that here, that's a restriction, but it's supposed to hold for all vectors and all components of the vectors. So this, we have to put this disclaimer. So without that disclaimer, it would fail. Well, here let's find the distance between A and B. Well, this distance, you can look at this as being the so-called norm of A minus B. So this is the norm here. If we take A in terms of 2, 3, the 1, and the 5, minus parentheses, the -2, 0, 3, and the 8. Well, that gives us the norm of 2 plus 2. So we get 4. 3 minus 0 is 3. 1 minus 3 is -2. And then 5 minus 8, -3. So we get the square root of 16 plus 9 plus 4 plus 9. So that gives us the square root of, just add those numbers up, that's 25 plus 13. So we get the square root of 38. Let the vector space have the inner product here given. This later on in linear algebra, this relates to what we call this inner product in terms of some Hilbert space. And then we can also talk about elementary Banach spaces as well when we look at its so-called norm. So here P is said to be 1. So this is the inner product of P with itself, and you take the square root of that. So this is the integral of -1 to 1. Well, P is 1, right? So we use that. So this is just 1 times 1. So this is 1 dx. Take the square root of all of that. So we just integrate. So in integrating, we get x evaluated from -1 to 1. That's the square root of that. So this is the square root of 1 plus 1. We get the square root of 2. So now the norm of Q is the inner product of Q with itself. Take the square root of that. So this is the inner product. Here Q is said to be x. 1/2 that. So this becomes the integral from -1 to 1 of x times x, x squared dx, all to the 1/2 power. Oh, my space is running out. So this is, we integrate, we get x to the 3rd all over 3. That's evaluated from -1 to 1. And then we're taking the square root of all of that. So this becomes 1/3 minus a -1/3. So it's 1/3 plus 1/3, square root of that. So this is the square root of 2/3. Okay. And then that last one, this distance of P and Q. This is the norm of P minus Q. This is the inner product of P minus Q with itself, raised to the 1/2 power. But P is said to be 1 and Q is x, so this is the inner product of 1 minus x times 1 minus x raised to the 1/2 power. And so this becomes the square root of the integral going from -1 to 1 of 1 minus x times 1 minus x. which is 1 minus x squared dx, and that's raised to the 1/2 power. We're trying to, between two functions, to find here their distance. If we can measure that distance for whatever value x as you travel from -1 to 1, is there a so-called maximum distance in relationship between the two functions p and q? What's the smallest? Well, we can use the norm to try to give us the so-called distance between the two functions. So here, let's simplify that integral. This is the integral from -1 to 1. 1 minus x squared, you FOIL that out. That's 1 minus 2x plus x squared. This is dx, and this is all, again, 1/2 power. And so we integrate. So this is x minus 2x squared all over 2 plus x to the third all over 3, evaluated from -1 to 1, and again the 1/2 power of all of that. So this becomes the square root of all this stuff. Evaluate these terms at 1, so this is 1 minus 1 plus a third, and then now minus all of these terms, x evaluated at -1, so this becomes minus 1, this plus 1, and then this becomes minus this minus, that's positive, x -1 to be squared, so that becomes here plus 1, and then this becomes minus -1 to the third over 3, so it becomes plus 1/3. So that 1 minus 1 cancels out. We have left 2 plus 2/3. So it's the square root of 2 plus 2/3. So this becomes 6 and 2 is 8 all over 3, or 2 times the square root of 2/3. You can leave it as the square root of 8/3. That's fine. All right, just very simple algebraic proofs to show the left side equal to the right side. We're going to start with all the big stuff on that right side and just break it down, just simplify it. So first, let's look at the norm of u plus v squared. Well, you remember this is the norm of u squared plus 2 times the inner product of u and v plus the norm of v squared, right? Now, comma, let's look at the norm of u minus v squared. This is the norm of u squared minus 2 times the inner product of u and v plus the norm of v squared. So now we take these two norms, take 1/4 and look at their difference. So we look at 1/4 times the norm of u plus v squared minus 1/4 times the norm of u minus v squared. So this is 1/4 times the norm of u squared, and then plus 1/4 times this 2, it becomes a 1/2 times the inner product of u and v plus 1/4 times the norm of v squared, and then that becomes minus all of these guys over here, so minus 1/4 the norm of u squared minus this minus becomes plus 2 divided by 4 is 1/2 the inner product of u and v, minus, sorry Charlie, minus 1/4 times the norm of v squared. And if you look at that, this is 1/4 the norm of u squared minus 1/4 the norm of u squared, they cancel out, and then 1/4 the norm of v squared minus 1/4 the norm of v squared cancel out. And so what we have left is this 1/2 the inner product of u and v plus 1/2 the inner product of u and v, and that gives us the inner product of u and v, right? Now part B, we just borrow from part A in terms of these norms that we already found, the norm of u plus v squared plus the norm of u minus v squared. Just write what it is and simplify, and you get what you need. This becomes the norm of u squared plus 2 times the inner product of u and v plus the norm of v squared, and then this is minus this, or plus, that is, the norm of u minus v squared. So this is plus the norm of u squared minus 2 times the inner product of u and v plus the norm of v squared. Now look at what cancels out. The inner products, they're just opposites of each other. And so what we have left is just the norm, do my adding right. This is the norm of u squared plus the norm of u squared. So this is 2 times the norm of u squared, right? That guy and this guy. And then we get plus 2 times the norm of v squared. So that works out just fine. All right. So here we want to find the cosine angle of these two polynomials. What is p? If I can just write the coordinates, this is going to be 0, 1, and -4. And then for q, 3, 7, and -3. 3, 7, and -3. So we want to look at the cosine. Remember, the cosine is defined. Cosine theta is equal to the inner product of u and v. So you got to find the inner product of u and v divided by the norm of u times the norm of v. So we got to find the norm of u, and then we got to find the norm of v. So the inner product of u and v, well, that's 0, 1, -4 dot product with 3, 7, and -3. So that gives us 0 plus 7 here plus 12. So we get 19. Now the norm of u is the square root of 0. Well, sorry, we're dealing with p and q. The inner product of p and q all over the norm of p times the norm of q. It's fine, but we can be consistent. One squared is 1 plus -4 squared is 16, so we get the square root of 17. And then the norm of q, that's the square root of 3 squared is 9 plus 7 squared is 49 plus 3 squared, that's 9. So there, that gives us the square root of 67. And so cosine theta is the inner product of p and q all over the norm of p times the norm of q. So this becomes the 19 all over the square root of 17 times 67. And it's on your calculator. It's just point, get close to it, 563. Okay. So just approximately. Are these polynomials orthogonal? Well, the dot product didn't give us 0. So here we say no, since the dot product or the inner product of p and q gave us 19 and not 0. Here, verify the Cauchy-Schwarz inequality for vectors. Well, what is that? The Cauchy-Schwarz inequality, you remember, it says that the absolute value of the inner product of u and v is less than or equal to the norm of u times the norm of v. It looks like a K, but you know it's the absolute value. Okay, so here we need the inner product of u and v. So this becomes 0 plus -2 times -1 plus 2 times 1 plus 1 times 1. So this gives us 4 plus 1, we get 5. Now the norm of u is the square root of 4 plus 4 plus 1. That's the square root of 9, gives us 3. Then the norm of v is the square root of 1 plus 1 plus 1 plus 1. That gives us 2. So we question mark, is it true that the norm of u, well, the inner product of u and v, excuse me, is that less than or equal to, and this is the absolute value, is that less than or equal to the norm of u times the norm of v? Well, let's see. Well, this gives us the absolute value of 5 is that less than or equal to the norm of u, which is 3, times the norm of v, which is 2, we get 6. So indeed, 5 is less than or equal to 6. Good. So that verifies. The last one, number 14, yesterday in class, folks, we just went over the Gram-Schmidt process, and I worked that problem, so I won't do it again. And my hand is tired. So I'm going to stop right there. Thank you very much.